Good evening, all. I am Pramod Kawal, TA of this course. So I am going to take a problem solving session 10 on the course Chemical Reaction Engineering 1 with 10 temperature and pressure effects. The professor, the course tutor is Professor Vishwada Mandal, the Chemical Engineering Department, IIT Guwahati. So I think all of you have gone through the week 10 lectures which are available on SEM portal. So starting from the MCQ 1, the energy balance equation over a tubular reactor under the transition condition is. Option are given an ordinary nonlinear differential equation, B an algebraic differential equation, C a linear partial differential equation, and D is a nonlinear partial differential equation. So option C is correct, means a linear partial differential equations. Question 2. An isothermal reversible reaction is being carried out in ideal tubular flow reactor. The conversion in this case will decrease in the space. Isothermal irreversibles means temperature constants. So here the conversion in this case will decrease or increase or whatever in a space. It's a decrease. Question 3. An exothermic reaction takes place in an adiabatic reactor. The product temperature reactor feed temperatures. Okay, the product temperatures. Here you have to fill the reactor feed temperatures. So is always greater than the reactor feed temperatures. Question 4. This space-time is equivalent to holding time in a steady-state mixed flow reactor for option given A for non-isothermal gas reaction, B variable fluid density systems, C constant fluid density systems, and D gas reaction with a changing number of moles. So the space-time is equivalent to holding time in steady-state for a mixed flow reactor for a constant fluid density systems. Moving to the question number 5. The temperature of the adiabatic batch reactor initially set at 398 Kelvin is being studied in the context of the reaction PQs. It is assumed that the heat generated by the reaction is minus 2.5 kilojoule per mole at the initial temperature of 398 Kelvin. And both the substance P and Q have a constant heat capacity. Of 95 joule per mole per Kelvin. Determine the final temperature read after achieving a fractional convergence. So we have to calculate the final temperatures after achieving the fractional conversion 0.95. So for here mentioned that adiabatic batch reactors. So for adiabatic batch reactor, the energy balance equations, with equations, Cp, Dt equal to S delta HR. Right. This is the heat of reactions into convergence. So we can write Cp is equal to T minus T naught. So you have to calculate the final temperatures. Yes, Cp. Right. Now heat of reaction given minus 2.5 kilojoules per 3 convert into the joule, and conversion given 0.95, and Cp given 95 joule per mole Kelvin. So T minus T naught equal to 25, right, in Kelvin. And initial temperature given 398 Kelvin. So T equal to 25 plus T naught is 25 plus 398 equal to 423 Kelvin. So 423 Kelvin. So in option given the degree Celsius. So convert in the degree Celsius. So 150 degree Celsius outlet temperature. Generally, outlet temperature is greater. Product temperature is higher compared to the feed. This is one MCQ questions. Option is D. I move to the question number 6. In adiabatic CSTRs, there is a reversible isomerizing reaction between the substance A and B, represented as this one's A gives B and B gives A. This reactor operates at specific condition. The forward reaction rate constant at temperature T of 323 Kelvin is 0.5 per hour, and reverse reaction rate constant at the same temperature is 0.3 per hour. The reactor feed consists of pure A with a molar concentration of 2.5 molar, a flow rate of 15 liter per hour, and initial temperature of 300 Kelvin. Both the compounds A and B have a same heat capacity constant of 250 calorie per mole per Kelvin. The standard heat of reaction for this process is minus 25 kilocalorie per mole. Given that the outlet fractional conversion is 0.5, determine the operational temperature of the reactor. So we have to calculate the outlet temperatures. Right. Reaction givens. So Cp, same heat capacity means Cpa equal to Cpb given 250 calories per mole into K. And delta H given minus 25 kilocalorie per mole. And Ca not given 2.5 mole per meter cube. Right. And flow rate given 15 liter per hour. And X given 0.75. Right. Now the rate equation for these reactions, so Ra equal to K1 Ca minus K2 Cb, right? So Ra equal to K1 K2. So we can write K1 Ca naught 1 minus Xa, right? And K2 Cb naught plus B by A. This is B by M is stoichiometric of component into XA into CA. Right. Now here pure fluid given and CB not equal to 0. So all the value given. So put in this equations. Like equation 1 minus RA equal to 0.5 into 2.5 to 1 minus XA means 0.25. 0.03 CB not equal to 0 plus 1 to 0.75 into 2.5, right? R equal to 0.2562 mole meter cube, right? Now energy balance. So Cp Ct delta HR Xa, right? So T minus delta HR Xa equal to Cpa plus P by A Cp T. So T equal to T naught plus distance. Okay. So put the value T23 plus 25 in the power 3 to 0.75 to 250 plus 250, right? Equal to 360.5 Kelvin. Right? Here is 223. Moving to the question number 7, what is the maximum allowable inlet temperature in Kelvin for a feed in adiabatic mixed flow reactor where an irreversible reaction takes place in a aqueous case, converting substance A and B into the product P. The feed consists of 4 kilo mole per meter cube each of A and B entering the reactor at the flow rate 7 meter cube per hour. To ensure that exist streams or temperature does not exist at 298. Given the following data that are independent of the composition and temperature. Heat of reaction given minus 115 kilojoule per mole. Density of the reacting mixture given 998 kg per meter cube and specific heat of the reacting mixture is 7.5 kilojoule per kg per Kelvin. So we have to calculate the inlet temperatures. So the concentration of initial concentration of reactant given 4 kilomole per meter cube and flow rate given temperature, the exist stream temperature does not exist at 298 kelvins. So inlet temperature, so you have to calculate the inlet temperature. So all of those are required parameters are given here. So, the adiabatic mixed flow diagram. 4 kilomole meter cube. Right. The temperature, so you have to calculate temperature Ti and T outlet 298. Right. And reaction given A plus B gives B. So by energy balance equations, Cp dt equal to minus H R into Vx. So here the Xa A not mentioned, so it means total conversion. 100% means 1. Right. So Cp dt equal to delta H R. Right. Now Cp given 7.5 kilojoule kilojoule per kg into Kelvin into meter cube 4 kilomole is 1 kilomole to 1000 mole into density 998 kg per meter cube. So delta T equal to minus minus 1 and it cancels 115 kilojoule per mole. Right? Mole it cancels. Per meter cube it cancels. Kg it cancels. Right. So delta T equal to 61.45 Kelvin. So to inlet temperature T minus Ti equal to 61.45 Kelvin. So T inlet to 236.54 Kelvin. The inlet temperatures. Question 8. What is the maximum allowable feed temperatures in a Kelvin for the adiabatic plug flow reactor where the liquid phase reaction A gives B? If the inlet concentration is 15 kilomole per meter cube, the density of the reaction mixture is 1270 kg per meter cube. The average heat capacity of feed stream is 7.48 kilojoule per kg per Kelvin, and heat of reaction is minus 70 kilojoule per mole of a reactant. The reactor temperature should not exceed the 598. The same question, but here change the reactor here plug to reactor. The previous one was adiabatic, sorry, mixed flow means CSTR. Right. This means same the energy balance equations with Cp dt equal to delta H given by the- take the unit kilojoule per kg into Kelvin. Kilojoule mole. Right. X is a 1. So here is a to balance the unit plus Cu mole per meter cube. One mole it cancel. Now kilojoule. So here is a kg. So multiply density kg per meter cube. Kg cancel balance. So density is P delta T is equal to Ca into HRA. All the value given, put in the equations. So T minus Ti equal to Ca 15 10 to the power 3. So 78 into 10 to the power 3 divided by density 1270 into Cp heat capacity 7.48 to 10 to the power 3. Right. So 123.16 Kelvin. Now calculate initial temperatures. We know the final temperature 598. So initial temperature 474.83 Kelvin. Here, question number 9. What is the maximum permissible fractional conversion of N2 plus 3 is to gives twice NH3 reaction in adiabatic reactor used for the ammonia production. The feed contains 2 kilomole per second of nitrogen and stoichiometric amount of hydrogen at the initial temperature of 1000 Kelvin. To ensure that the adiabatic temperature rise in the reactor does not exceed 298 Kelvin, calculate the maximum allowable fractional conversion. Assume ideal gas behavior for the feed and product stream and heat of reaction given at 1000 Kelvin is 6000 joule per mole. Additionally, consider the mean molar heat capacity Cp in the range 1000 to 1200 Kelvin, which are 0.053, 0.0829, and 0.0361 kilojoule per mole per Kelvin for the nitrogen, hydrogen, ammonia respectively. So we have to calculate here the fractional conversions. So here 200. Right. Into S2. So here to feed fluoride reagents to kilomole and mention that stoichiometric amount of hydrogen means 6 kilomole per second. Right. And temperature is 100,000 degrees. And final into n is to 2 minus 6, right? Kilomole per second, temperature 1200 kelvin. Reaction method that the outlet temperature does not exist at 200 kelvin, so it's a 1200. Right? 3 minus 6, 6 right? Kilomole per second. Reaction given N2 plus 3S2 gives twice NH3. Right? So the extent of reactions alpha equal to initial final mole minus initial moles divided by stoichiometric coefficients. So here final mole 2 minus x initial 2 divided by minus 1 for this is for the n2 of x kilomole, right? This is for the n2. Now energy balance equations Cp dt equal to minus delta H or Ex into x. Okay, heat of reaction thousands right into x and alpha okay, 1 minus 2 minus x into 0.053 projects. So Cp dt the extent of reaction equal to minus hr x into x right. So delta H are given. So 6000 into x, right? So 2 minus x into 0 heat capacity for into 10 I use 3 thousands convert into kilojoule into joules. 1000, right? Plus 3 minus 6x into 0.0829 hundred into 1000 is to temperature is 1200 minus 1000 200 plus twice 6 to 0.0361 into 1000 to 200 equal to 6. So calculate the x. So x is 59.36%. Right. So thank you all. I covered all the questions based on the 10th chapters. So we will meet on next Friday on next chapters. Thank you.